Hi, my name is Weiming. Today I will present the paper Joint Optimization in H-Cloud Continuum for Federated Unsupervised Person Re-Identification. I will start with background and challenges of person re-identification, followed by the existing solutions. I will then present our proposed solutions and experimental results. Person re-identification is an important computer vision task. It aims to re-identify a person from non-overlapping camera views. Person ReID has attracted considerable research interests due to its wide applications in public security and emerging applications in retails. The majority of these applications heavily rely on centralizing a large number of images from diverse sources to train deep neural networks. However, data protection regulations such as GDPR and CCPA have been published by various states and countries to regularize personal data collection. Training images of person ReID could contain sensitive personal information, such as personal identity and location. It becomes infeasible to centralize a large number of these images to a cloud server to train deep neural networks. Federated learning is a potential solution to solve this problem. Federated learning is an emerging privacy-preserving distributed training method. Different from traditional centralized training, federated learning shares model updates from clients to server instead of raw data. It is intuitive to implement federated learning to person ReID to train models collectively from decentralized edge devices. But it faces the challenge of statistical heterogeneity. Since data is collected from cameras in different locations, their data distributions and data volumes are different. Our previous work, FedUReID, addresses this problem and optimizes its performance via benchmark analysis. However, our previous study, as well as the majority of the federated learning methods, rely on data labels. While images are unlabeled when collected from street cameras, annotating this data is expensive, laborious, and time-consuming. For example, 3 annotators need 2 months to label around 4,000 identities from 180 hours of videos. To address these problems, we propose a new federated unsupervised person ReID system, namely FedUReID. FedUReID system learns person ReID models without any labels while preserving privacy. We designed 3 flows to form an end-to-end training pipeline: training flow, control flow, and clustering flow. In these 3 flows, we address the statistical heterogeneity among decentralized parties via joint optimizations of cloud and edge. These optimizations include personalized epoch, personalized clustering, and personalized update. Before explaining them in detail, let's understand the training process of the system. At the start of the training flow, the server initializes a model and distributes it to client. For each training round, the server and clients collaborate to train models with 4 steps. First, local training. Each client conducts local training to train local models. The architecture of the local models include a backbone and a classifier. Second, model upload. Each client uploads the backbone models to the server. Third, model aggregation. The server aggregates these models to obtain a new global model. Fourth, model update. The server updates clients' models with the global model for the next training round. One of the key questions is how do we conduct local training without any labels? We adopt hierarchical clustering as the clustering flow to predict pseudo labels for unlabeled images after each training round. The figure on the right illustrates the process of hierarchical clustering. Assuming that we have 8 images in total, each image is treated as a cluster at the start of training. So we assign a unique label 1 to 8 for each cluster. After each training round, we merge 2 clusters based on the similarity of their image features and then reassign pseudo labels of these images. After that, we update the dimensions of the classifier to be the same as the number of clusters. In this way, we can adaptively predict the labels of these images until no more clusters can be merged. In this example, we merge 25% of clusters in each round, and we use such implementation as the baseline in the experimental results. But due to statistical heterogeneity, this intuitive baseline implementation causes 2 problems. Firstly, Using the same local epoch leads to inappropriate computation assignment in different clients in different training rounds. Secondly, using the same merge percent leads to inappropriate clustering paces among clients. To tackle these two issues, we propose personalized epoch and personalized clustering in ages. We first propose personalized epoch to reassign computations through our training by dynamically adjusting the number of local epochs of each client in each training round. For the first training round, we use a larger epoch to warm start the training. After that, we only assign enough computation to each client to reach good enough computation to reach good enough training precision. Particularly, we designed a controller to retrieve training feedback of each batch. It early stops the training when precision of any batch of training equals to 100% or cumulative average precision is larger than 95%. In this way, each client uses personalized epoch depending on their training results. Secondly, we propose personalized clustering. We argue that clients shouldn't use the same merge percent for clustering. Here we analyze the problem of using the same merge percent. Since clients have different numbers of identities and images, using the same merge percent causes clients to reach the number of identities closest to theirs at different rounds. For example, as shown in the table on the left, the number of identities is closest to the actual numbers at the 19th round for Duke dataset, but at the 10th round for Viper dataset. The accuracy drops after those rounds because some labels are wrongly classified. As a result, clients will achieve the best performance at different rounds, and the aggregation results of these clients will not be optimal. One solution is to use the actual number of identities to calculate clusters to merge for each client by using the formula on the right. NK is the total number of images, IK is the actual number of identities, and R is the fixed total training rounds. But this method is not practical because the actual number of identities is unknown as data is unlabeled. Hence, we designed a provider to estimate the number of identities of clients. Before local training of the first round, we profile the clients with a small local epoch for several training rounds and retrieve the round that reaches the best performance. And then we obtain the number of clusters of that round as the estimated number of identities and calculate the clusters to merge using the formula. As we can see from the table, that the number of identities approximates the actual number of identities of clients. As a result, each client can calculate their personalized clusters to merge using these profiled results. Last but not least, we propose personalized update in the cloud. The server first aggregates the backbones uploaded from edges via weighted average. After that, instead of simply replacing clients' local models with the global model, we update the local models of clients via linear interpolation of global model. The decay rate mu depends on the layer-wise similarity of local and global models. The intuition of calculating mu is to increase the importance of local model when the local model is not similar to the global model. As such, the updated local model theta kr plus 1 retains more historical information of local model, which is more personalized to the data in the client. Next, let's look at the experimental results. We construct training with 8 commonly used person ReID datasets. This table shows the statistics of these datasets. They have large variances in the number of images and identities. The figures on the right are samples of these 8 datasets. They are collected from cameras facing different angles under different lighting conditions and at different locations. This dataset simulates statistical heterogeneity with these variances. We compare our proposed FedUReID with other methods and the baseline. FedUReID with joint optimizations outperforms the baseline and other existing methods on the 2 largest datasets. Besides, it also outperforms standalone training and the baseline on 8 datasets. Standalone training here means that training in one client without labels using hierarchical clustering. Moreover, we also conduct ablation studies of the optimization methods. Each single optimization outperforms the baseline. The joint optimization generally outperforms single optimization. Last but not least, we compare the computation cost of these methods. Although we need extra computation to profile clients for clustering, the overall joint optimization actually reduces the total computation cost. In conclusion, we propose a new federated unsupervised person ReID system with joint optimizations of cloud and edges. We hope that this work will encourage the community to explore more on purely unlabeled scenarios in federated learning. Thank you, and we will release our implementations and datasets in the future. You are also welcome to contact me if you have any questions.